Seafloor spreading at divergent boundaries. The greatest volume of magma, more than 60% of Earth's total yearly output, is produced along the oceanic ridge system in association with seafloor spreading. As the plates diverge, fractures are created in the oceanic crust that fill with molten rock that wells up from the hot asthenosphere below. This molten material slowly cools to solid rock, producing new slivers of seafloor. This process occurs again and again, generating new lithosphere that moves from the ridge crest in a conveyor belt fashion. Seafloor spreading occurs along relatively narrow areas located at the crest of oceanic ridges. Below the ridge axes, where the lithospheric plates separate, solid, hot mantle rock rises upward to replace the material that has shifted horizontally. As the rock rises, it experiences a decrease in confining pressure and may undergo melting without the addition of heat. This process, called decompression melting, is how magma is generated along the ridge axis. Partial melting of mantle rock produces basaltic magma having a composition that is surprisingly consistent along the entire length of the ridge system. This newly formed magma separates from the mantle rock, from which it was derived, and rises toward the surface in the form of teardrop-shaped blobs. Although most of this magma is thought to collect in the elongated magma chamber reservoirs, located just beneath the ridge crest, about 10% eventually migrates upward along fissures to erupt as lava flows on the ocean floor. This activity continuously adds new basaltic rock to the plate margins, temporarily welding them together, only to be broken as spreading continues. Along some ridges, outpourings of bulbous lavas build seamounts, submerged shield volcanoes, and elongated lava ridges. At other locations, more voluminous lava flows create a relatively subdued topography. During seafloor spreading, the magma that is injected into newly developed fractures forms dikes that cool from their outer borders inward toward their centers. Because the warm interiors of these newly formed dikes are weak, continued spreading produces new fractures that tend to split these young rocks roughly in half. As a result, new material is added equally to the two diverging plates. Consequently, a new ocean floor grows symmetrically on each side of the centrally located ridge crest. Indeed, the ridge systems of the Atlantic and Indian Oceans are located near the middle of these water bodies. However, the East Pacific Rise is situated far from the center of the Pacific Ocean. Despite uniform spreading along the East Pacific Rise, much of the Pacific Basin that once lay east of this divergent boundary has been overridden by the westward migration of the American plates. When the concept of seafloor spreading was first proposed, upwelling in the mantle was thought to be one of the driving forces for plate motions. Geologists have since discovered that upwelling along the oceanic ridge is a passive process. Stated another way, mantle upwelling occurs because space is created as the oceanic lithosphere moves horizontally away from the ridge axis. Spreading rates and ridge topography. When various segments of the oceanic ridge system were studied in detail, some topographic differences came to light. Many of these differences appear to be controlled by spreading rates. One of the main factors controlled by spreading rates is the amount of magma generated at a rift zone. At fast spreading centers, divergence occurs at a greater rate than at slow spreading centers, resulting in more magma welling up from the mantle. As a result, the magma chambers located below fast spreading centers tend to be larger and more permanent features than those associated with slower spreading centers. Further, spreading along fast centers appears to be a relatively continuous process, where rifting and upwelling is occurring along the entire length of the ridge axis. By contrast, rifting at slow spreading centers appears to be more episodic, where segments of the ridge may remain dormant for extended intervals. At slow spreading rates of 1 to 5 centimeters per year, such as occur at the mid-Atlantic and mid-Indian ridges, a prominent rift valley is present along much of the ridge crest, and the topography is quite rugged. Recall that these rift valleys can exceed 30 kilometers in width and 2,000 meters in depth. The upward displacement of large, buoyant slabs of oceanic crust along nearly vertical faults produces the steep walls of the rift valley. In addition, at slow spreading centers, volcanism produces numerous volcanic cones along the rift valley, which enhance the rugged topography of the ridge crest. Along the Galapagos Ridge, an intermediate spreading rate of 5 to 9 centimeters per year is the norm. In settings such as this, the rift valleys that develop are shallow, often less than 200 meters deep. In addition, their topography tends to be subdued compared to ridges that exhibit lower spreading rates. At faster spreading rates, greater than 9 centimeters per year, such as occur along much of the East Pacific Rise, rift valleys are generally absent. Instead, the ridge axis is higher than the ocean floor on either side. Such areas consist of swells, volcanic extrusions that tend to overlap or even produce relatively narrow structures. In other places along fast-spreading centers, sheets of fluid lava have produced areas of relatively subdued topography. Because the depth of the ocean depends on the age of the seafloor, ridge segments that exhibit faster spreading rates tend to have more gradual profiles than ridges that have slower spreading rates. Because of these differences in topography, the gently sloping, less rugged portions of the oceanic ridges are called rises.